Yeah, so thanks for having me. This talk is about Pier. There are currently many ways to build a Haskell project. There's generic ones like Make and Nix and Bazel, which is a tool open source by Google. And there's Haskell-specific ones. The two most well-known are, of course, Cabal and Stack. But there's some other ones like Mafia, which was developed originally at Ambiata. And in my work recently, I've been using Nix, Bazel, and Stack and had issues with all of them. So I did what any software engineer would do and wrote another one, which is called Pier. So what is it? So in purpose, it's most similar to Stack. So individual packages are configured with Cabal files, and the entire project is configured with a Pier.yaml file. Packages are downloaded from Package. It uses Stackage, just like Stack, to get the versions. Stackage has YAML files with, there's a list of, for each package, what the version number is, and you get them to be consistent. And then Pier also downloads and maintains its own local installation of GHC and takes the version number to be consistent with the Stackage build plan. Okay, so then how does it differ? It differs in a couple ways. The first is that if you look at how Stack is implemented, it actually calls down to Cabal, the library, for a lot of its implementation in terms of how it calls GHC, and does this at a course level, like calling a configure step and a build step. In contrast, Pier implements all that logic nearly from scratch. It only uses Cabal, the library, for parsing the Cabal file format, because why re-implement that? But everything else it does from scratch, and it calls tools like GHC and GHC-PG directly. The other main difference is in how its build system is implemented. Stack implements its own build system, its own detection of when files have changed, its own dependency management, walking down the dependency tree. Pier uses Shake, which is a Haskell library that's generic for writing build tools. There's going to be a talk on it tomorrow, or at least partially involving it at ICFP. And in addition to using Shake, I wrote a layer on top called PeerCore to just more easily manage build inputs and outputs. Interestingly, the very first version of Stack did use Shake, and then they moved away from it soon after. There's a couple interesting blog posts about this, but my takeaway is because Stack operates at this course level, they didn't have as much need for the dependency management that Shake provided. So Pier, by operating at a different level, provides, I think, an interesting alternate design point. Okay, so I'm going to tempt the gods and do an actual demo. All right, is that visible enough to people in the back? Fair. Okay, so this is a very simple, I'm going to show a demo of how Stack works on a project and then show Pier. So that's not big enough. Here. Okay, so this is a simple Stack YAML file. It specifies a resolver, which ties it to specific package versions, and there's two packages, foo and bar. Foo package is very simple. It just has a library that depends on just base and text. And bar has a library that depends on foo, and then also has 3 executables. So there's an executable that just depends on base and text and depends on neither foo nor bar. There's an executable that depends on foo, and an executable that depends on bar. So if I say stack build bar exe depend on neither, what you would want to happen is it should just build that executable and not build any of the libraries since they're not necessary. Let me just wipe out everything first. And so starting from nothing, unfortunately the very first thing that it does is it builds foo and then builds bar and then builds all 3 executables, even though we only asked for 1. This actually isn't a bug. This is intended behavior. As you can see from this output message, because Stack is operating at this indirection through Cabal, it has to run the full build once in order to get all the metadata. And then once that's done, it has the metadata and it can build just the binaries it wants. Well, in theory, so if I say edit a file under foo, and let's just change this to something else, and then I do a rebuild, this doesn't depend on that file, so it shouldn't cause anything to happen. But unfortunately, it unregisters both bar and foo and then starts building everything again, although it does just build that 1 executable. And again, I think this is due to this indirection. There's a limit in how fine-grained it can handle the build. Okay, so if we do instead Pier, so the command line tool, just wipe out everything and then say Pier build bar exe depend on neither. So it starts by, like stack, there's a shared cache under the home directory with things that have already been done that I set up. So it's already downloaded GHC, it already has a local installation, it parses the build plan, it sees it's already downloaded stack, and then all it does is just build the bar executable. And if I build, depend on.
It says building library text. It didn't just build library. It didn't just build text.
No, so everything in parentheses is pulled from a shared cache.
Okay. Right.
Yeah, and so showing something a little non-trivial, say depend on foo, then you'll see it'll build foo and then build the executable they wanted, but not the bar library. And if I change this back, then you can see it builds it again. And if I change this back, let's do this, then it actually sees that it's already been built because Pier actually remembers all the previous things that you built and can just reuse a thing from the cache.
And if you enable profiling? Profiling?
If you enable profiling, then it will it'll keep two versions.
Okay.
Yeah. So more precisely, like if you Pier which will tell you the location of it, and so Pier stores everything in this underscore Pier directory. So you can see there's some shake metadata that's stored, and also the artifact, which is something specific to Pier, and it stores it in this. Let me get this whole thing on the screen. There you go. So it has this hash, and then if I change this to the other version and then run it, so then it says, okay, you've already built this, here's what the output has in a different hash. And to be done with this first, you can say Pier run, and I can say this to something with either more O's, and Pier run, and then it'll rebuild everything automatically from the run command. Okay.
Does it support backpack?
Not yet.
Okay.
So you compare, like in terms of file management, how stack works. So there's a .stackwork file at the top level, but then there's also like separate .stackworks that stack puts in a bunch of different directories. So again, like Pier just tries to make the output file management a little nicer. And so for my last demo, I will build a lens package, so which is sort of notorious for having a lot of dependencies. And so I just prove to you this is running in parallel with which Shake makes really easy and uses all 4 CPUs. The way it starts is it just downloads the package tarball and then unpacks it, looks at the cabal file, sees the dependencies, and then continues down that build chain. Currently, it's not actually using the cabal package index because that's not necessary. It also adds some simplifications. This also, you might have noticed it went through really fast. That's because it's building without optimizations. And so hopefully, or at least by default, and if you want, you can enable that.
Is this something equivalent to the cabal solver that's trying to figure out which version of each package to build?
It doesn't need to. So it's using the stackage build plan. Oh, okay. So stackage has already done that for it. Yeah. And that's, again, why it's so fast. Cool. And so that finished in about 50 seconds. Cool. So
is it building in source file injection mode or -- make mode? Is it
it calls GHC -make currently. Yeah. So it's compiling everything in a package with one invocation of GHC.
Yeah.
Okay, going back to the slides. Okay. So, yeah.
Sorry, you said one invocation of GHC, so is it not getting any parallelism except for the GHC-make-j level?
It's within a package, it's currently building sequentially, and then between different packages, like different dependencies of Lens, it's building those in parallel. And that was the core usage you saw before. It would be interesting to add -j to this, but it would be a little harder to square that with how Shake's parallelism works, so I haven't thought that through yet. Okay. So in order to make the implementation simpler, I wrote a layer called PeerCore, which abstracts away some stuff from Shake. Its design is motivated by tools like Nix and Bazel in a few ways. The main one is that output files are managed automatically in Shake by default. It's sort of up to you how you want that organization to happen. The Build files are hermetic, build steps are hermetic, meaning that when you run a process, it's run in a temporary sandbox with an explicitly declared set of inputs and outputs. This is pretty similar in purpose to what Cabal new build is doing, but this is intending to be a generic thing, not just for building Haskell stuff, this library layer. And then finally, the build logic can be written in a forward style, meaning you can say, do this, do this, do this, rather than like a make file where you say, here's the output, this is what its inputs are, and this is how you do it, and requiring on that to wire everything together. So I want to talk a little about the Haskell library part of it. So the main type is an artifact, which is just a file or directory that's being tracked by Pier. It's one of two things. It's either something that's user created with the external function, or it's something that's built by Pier with the run command function. This function runs in the action monad, which is something that Shake provides for dependency management. And so this integrates with any other Shake rules that you have. And indeed, I wrote other things using normal Shake, but I use this for a lot of the details of it. So this takes two commands. One is, two arguments. One is the command, which is what to execute in a sandbox. And the other is, once you're done, what is the path of the output? So more specifically, a command is one of two things. It's either a command input that adds an artifact to the sandbox, or it's prog, which is an invocation of a command line program to run it in the sandbox. And a command is a sequence of these things, so you can combine them with monad or semigroup. And so run command creates a temporary sandbox directory, runs the command within it, and then assumes that there's going to be some output file that's created, which is the file path argument. And so it takes that from the sandbox and it copies it to its final location, _Pier/artifact/hash/output, where the hash is just computed from the command, those list of entries, either the progs and or the inputs, the process invocations or the input files. So this abstraction saves a lot of build logic. If you compare Hadrian, which is a Shake program used to build GHC itself that was mentioned earlier today. So Hadrian has its own convention of an _build directory. And then within it, if you look at, for example, the base library and where it's stored in a file path that depends on the stage number and the name of the library and the version number, but doesn't include other build parameters like, say, the optimization level or maybe the profiling level. That might actually be part of the extension, I'm not sure. And so those are decisions that you have to make explicitly, whereas if you're going to say, OK, we'll squash this all into the hash, then that saves work when just trying to implement your build system. So as I said, run command stores its output per project in this _Pier directory. It also mirrors the output files into a shared cache under the home directory, which is what we used when Pier ran the very first time in the demo under home.pier. And it uses hard links so that you can save space and you can wipe out that cache and it won't affect any of your local builds. And then when run command runs again, if the same hash is used, then that file will already be on disk in one of those two locations. It can just reuse it rather than having to start everything from scratch. As I said, the hash, or this whole library is not specific to building Haskell code. So local packages and external packages are stored in the exact same way. That means that local packages can be shared between projects, which is different than how Cabal and Stack work, where they only share external package dependencies between projects, not local packages. Okay.
Just have to share cache.
I don't have a good story around garbage collection yet. And so if I did, then probably that would be the right answer. And you'd have something that looked more like Nix, say. So actually, yeah, let's move on. So simple code example for the run command function. So it's going to have two arguments. The second one is the command that you run in the sandbox. This is just an example for compiling a C source file, like a .c, and turning it into a .o just by calling GCC on it. So you're going to say, I want to include the source file in the sandbox, and then I want to run GCC and pass it flags for what the input and output are, and then specify what is the output and pass it to run command so it can store it in the final location. And something interesting to note is that the output file base name doesn't depend on the source file, which is a little weird until you realize that the hash actually depends on the input. And so the hash is already unique, and you need to make the output file. Like you don't also need to include that in the base name.
Does it depend on the path of the input file or the content of the input file?
It depends on ultimately on the content. So this input file could be either a user file, like in which case it'll depend on the contents, or it could be something that Pier's generated, in which case it'll depend on everything transitively all the way. Yeah, go ahead.
When you said it's sandbox, so on Unix systems, this is running inside a root?
It's not. I'm not doing a root yet. It's currently only just in terms using temporary directories, but I would like to make it like more real sandbox. So the other code example I wanted to give was just of composing these things together. So not just compiling, but also one file, but compiling several and linking them together. So if imagine you had 3 files, foo, bar, and baz, that you wanted to link together, then you map the external function over them, which gives you references, artifacts in the CS variable. Then you can map the compile function over them using 4p, which is a function that Shake provides, which just runs them in parallel. And that and using however many threads you have available on your, or how many CPUs you have on your machine. And that gives you a list of .o artifacts, and you do one final run command, and that gives you the final binary where you input, as input into the sandbox, you need all the .os, but not the .cs. And then you want to call GCC and give it the path to all those O's. So when this is run the first time, it'll compile each file separately and then link them all together. And then when it's run again, it'll only run the steps that are necessary based on which of those files have changed. Okay, so in terms of status, Pier is still experimental, but it can build most of Stackage already. Namely, of the 2,300 packages or so in it, it can build more than 90% of them. It can also build itself, which is a nice milestone. And the remaining issues form a long tail, but major issues include that custom setup scripts are not supported because of the, they're so tied to how the Cabal, the library, and how Cabal data structures work. I'm gonna skip the other one for time. Just build performance. In a simple example where I just build a split package involving setting up all the download of GHC and everything, then build Lens, which has about 30 dependencies, and then build Pier, which has about 100 transitive. And Pier is performing maybe 10% better than Stack. But if I build it without any optimization, then building those packages, Pier is twice as fast. I'm not exactly sure why, so take these with a grain of salt. But I think it's just because of this indirection, there's extra steps that Cabal has to do. And I think it's also like Shake might be doing better scheduling of the parallelism. I'm not sure. So in conclusion, please try Pier. It is on GitHub. It's in Stack Nightly and also on Hackage. PeerCore is also available as a library to try out, although it's a little more rough edges at the moment. Some future plans involve adding more commands like a REPL and haddock, adding backpack, as someone mentioned, managing the artifact store, for example, doing garbage collection, and finally maybe streamlining PeerCore and potentially merging some of all of it back into Shake. So thanks.
Right, can the Cabal that's present here take questions on that?
I have a couple things, but I think they're pretty quick. So you said you support like the Stack YAML. Does that also support like Stack snapshots as well, like custom snapshots? It's like a separate resolver where you can like override certain things and whatnot.
It probably doesn't yet, I think, but there's probably no reason why it couldn't.
Yeah, and is HPAC supported or maybe in the future?
Yeah, I would like to support it in the future, but unfortunately, I would basically need to re-implement HPAC in some sense because it's an executable that depends on what your source files are present. Because I'm doing everything with sandboxes, like I need to know ahead of time what the files are, like what files are necessary, and so it's fairly involved. But it would be nice because Pier itself is developed with HPAC, and so that's one of the barriers to developing Pier with Pier.
Yeah, and sorry, last thing, the hashes seem like, is there any chance you could use like a binary cache like Nix does or something like that?
Yeah, I would like to. I would like to make it more less janky, for lack of a better word. Just future work.
But even like a distributed one.
I would. The main barrier is that if the Haskell code changes, like, or if I ever want to change like the command file format, then you need to be careful about like changing what the hash is. You know.
Sure.
All right.
Is this for using your own GHC installation?
Yeah, so you can put a thing in the YAML file and it'll, like Stack does this too, if you say system GHC true, then it'll just use whatever's in your path.
And what is a specific GHC? So I'll build my own GHC.
I think, like, right now it only looks for it on your path, but like, that's a feature that could be added. Yeah.
Is there any plan to support using the Cabal install solver or any kind of solver at any point? Is that something you envision happening for this tool or not?
I think it's an interesting thing. It's low on the list of priorities,
Okay.
but it's also, once you have things that are stateful and depend on the state of the internet, then it becomes a little harder to manage. You would have to have a thing that says regenerate your state or have like package lock files or something. But in principle, it's something I think that could be done if there was enough interest.
The other question I was wondering about when you described, I thought the use of smart links was pretty cool, but if you ever like blow out your global package cache, right? So it seems likely that it wouldn't actually delete anything because the per project ones are also are linked to the same file. But then it seems like in like separate projects, when you started like building your dependencies anew, that you could end up in situations where you actually built the same thing twice. Then it was just like you had hard links to different places. I wanted to make sure I understood that.
So in the situation you're talking about, the second project will rebuild anything that was already built in the first project, and then add those back to the shared cache.
Yeah.
But if their files are already there, it'll use it. There's a danger that those aren't compatible. If, for example, GHC's behavior is not completely deterministic. But I haven't encountered that in practice yet.
Okay, just one more question, maybe?
So in the core of your build system, what was the reason to choose to shake over improving support for Bazel, using Bazel as the engine to build Haskell? You mentioned Bazel and Nexus too.
Yeah, so Bazel is really good if you want a polyglot build system, but if you're trying to just build Haskell, then the Stack's UI is better. For example, in terms of managing the REPL and other things that are more closer to it. The Bazel stuff has some hacks around it, or the file organization is different. Bazel also has difficulty with actions that depend, whose behavior depends on files on disk. They have limitations built into it that Shake doesn't have. There's actually that's the point of the talk that's going to be tomorrow in terms of what Shake does that Bazel doesn't.